So we were talking about pipes, piping systems and so on, general information, what they're used for, what's our interest in them, how do they work, several sizes, materials and so on. Now let's check out on models. When I say models, it's technically the mathematical models we use in order to relate the pressure drop. So this will depend on the type of fluid we have, either liquid, gas, or we can even treat solids. If we are piping them, you can treat them as fluids, for instance, sands or muds. So typically, as stated before, we are interested on the drop in pressure. We are, let's say, in the study of how do we avoid pressure drop. Should we decrease the diameter? Should we choose this material or this other material? And of course, typically you're also interested in if you have isothermal flow. Well, this piping material has these conditions, but then you will have this pressure drop and so on. So that's the overall idea on models. So let's see the liquid model. This is one of my favorite ones and the easiest one because you either have laminar flow, which is at slow velocities. They are so nicely arranged. There is no chaotic flow rate. And we have the most common one, turbulent flow, which is arised at high velocities. There will be plenty of chaos. There are whirlpools, some eddies, and so on. And let's see here. What we're going to see is that liquid or pressure drop is achieved due to friction. So the more friction you have in the pipe, the more pressure drop you will have. And why is that important? Because pressure drop implies energy loss. And what does that mean? Is that you will need to buy a pump and you will need to invest and pay pumping cost. We are going to talk about Reynolds number, which relates viscosity of the fluid, density of the fluid, velocity of the fluid, and diameter of the pipe, as well as the material or the roughness of the material. So this is the friction factor, which typically relates the friction losses. Now, as you can see, laminar flow, actually let's go back. Let's go direct to friction factor. What's the friction factor and what is Moody's chart? So friction factor was formally defined by Moody as the drop in pressure times the diameter of the pipe divided by the length of the pipe, the density of the fluid, and velocity of the material or the material inside the pipe. Fanning did the same, which actually both have similar conditions, drop in pressure, diameter, velocity, and so on. The only difference is that this is related by 4x. So just be sure that if you're using Moody's diagram, which is right here, use this definition. And if you're using Fanning's diagram, use this definition right here. So let's see how we read this right here. So we got the friction factor, which is present right here. The higher the factor, the higher the friction you will have. You have relative roughness, which is nothing more than the diameter and the roughness of the pipe. The more rough you have it, the higher roughness you will have. The lower you have it, well, the lower friction factor you will get. And one important part right here is the Reynolds number, which maybe you will say this is counterintuitive because Reynolds number relates directly with velocity. Now, as velocity increases, the friction factor decreases drastically. And maybe you will say, well, if we have high velocities, that implies high friction losses. And that is true, but for the friction factor, it's not. Remember that friction factor will be later on relating velocity, and typically, as stated before, as velocity increases, we have the square of velocity. So even though the friction factor might be decreasing, the velocity is increasing by a power of 2. So let's say we got a friction factor. Let's say we have a very smooth pipe. It's new, a top of the line material. We will be using then this line right here. Then we relate to the diameter. Let's say we got here. So the friction factor will be at a Reynolds number of 10 to the 5 power, which is right here. You should have a friction factor about 0.018, maybe 19. And then you will be able to relate that to your friction factor losses. Okay, so this is for the liquid. Let's go back. Let's see how do we do for gases. And actually we are analyzing incompressible flow. So let me just give you a very overview of the gas vapor transport. So typically we treat them as long nozzles, either isothermal, which implies that let's say we have here outside temperature. The outside temperature is 25 Celsius, so that will be isothermal. So they are moving in an isothermal ambience right here. We got adiabatic, so as stated before, you can cover, actually, no, this is not, but you can cover this with adiabatic material in order to avoid the transfer with the atmosphere. Maybe you want to keep it at, maybe this is at 50 Celsius. You don't want to lose those 50 Celsius with the ambience, which is 25 Celsius. You don't want to have your final piping product at 30 Celsius. Maybe you want to keep it maybe at 45. Then that will be a adiabatic flow. And isentropic flow, we're going to cover that later on. Right now, you just need to know that this is at the same entropy. So what we want to do is to avoid condensation and flashing. If you are transporting liquids, what you don't want to do is that they get so heated that they will vaporize in the pipe, and vice versa. If you have a vapor, what you don't want to do is that the vapor cools down and it condenses, because then you're going to have problems with the piping system. And finally, solid transport. I stated before that you can move muds or sands, but actually what we do with solids is move via trucks or move via these bands right here, or conveyor bands. So I like to call these discrete particles, because actually you're moving particles, even though you may say they are rocks or maybe small powder, but what you're doing is moving it individually through the conveyor right here. So these are the models: liquid, gases, and solids. What we're going to cover mostly is liquid and pressure drop. Gases are also covered, but we're going to see that later on.